when you come in, it'll cover just what we do today. I decided since the multiple choice is such a large portion of your test, okay, at 87% or whatever it is, like it's a lot, it's not that much, but 67, that we would do Unit 2 today, all right, focus primarily on multiple choice. Unit 3 tomorrow, primarily on multiple choice. And then on Monday, we're going to take another practice test in class, just the multiple choice portion, that first 80-minute portion, okay? We're going to do it online, so you're going to need a device, all right? You're going to need, it'll be on AP Classroom, all right? But you'll need an iPad or a computer, okay? You can't do, it doesn't work as well on your phone. You can do AP Classroom on your phone, but it just doesn't work as well, okay? And then the next day, that's APUSH, right? No, that's GEO. Okay, so on that next day, I'm going to talk through the free response questions, all right? All 4 of them, what they look like, show you some examples. If you miss, it's okay. I'm going to record the video, all right? So you can go in and look at the explanations and see what's expected in terms of the work. And then the next day, when you come back, so Wednesday, Thursday, we're going to finish up the multiple choice and the free response that are left in terms of that, okay? And then Friday's a non-instructional day. All right, so I won't see you at all on, well, I may see you, but it'll be crazy day. All right, and y'all have APUSH that day, right? So that's on Friday. Monday, we should all be here Monday. Okay, now I know next week there are lots of fun things going on. I need you in the room. Okay, I need you to just say no. All right, I talked to Mr. Russo. He and I talked this morning. Okay, I know you guys are amazing. You have wonderful opportunities to go and be at field days and do all these things, but we have an AP test in 7 days. Okay. And I need you in here if you're not taking an AP test. Okay? So I don't often say, please don't go, but I'm begging you, please don't go.
So next Friday's a non-instructional?
Yes.
Why is it?
We're doing class tournaments, teachers versus students. We're doing bubble soccer. We're doing talent show. So third block is the only block that we don't have something planned, but we won't be teaching during third block. So. Okay, and I haven't heard word, but typically on non-instructional days, they do still take attendance. So, but since y'all can't be exempt, okay. All right, that's all I'm going to say about that, okay? Ooh, and it was recording. I did not say that.
No.
Okay, no, I would never say that. But, okay, you do you, boo, is all I'm going to say. All right, about that. So that's on Friday. And then Monday will be our last day, okay, where we'll just kind of do last-minute things. I give my God and Country speech, and then we're ready. Okay, so that's what we do, okay? But that's kind of the plan, all right? Okay, so let's jump in here. Hallie noticed that some of the questions look familiar, okay? I have been pulling those from the practice test that you've already taken and one that you've not taken. And then yesterday we found out, late last night, I got an email, they have released the 2024, the actual questions from the 2024 exam last year. And they're in AP Classroom, so I will start to use those as well, okay? So to give you the most recent data that we have in terms of what questions are going to look like. All right. So let's take a look at this one. This was one that was kind of missed quite frequently on the actual practice exam for us and across the country when they wrote it. But anyway, so it says it has a whole at x equals 2. So what is that going to mean in terms of the function? Yeah, there should be an x minus 2 in the numerator and the denominator. And if we look, that happens in the first 2. So I can definitely mark out the last 2. Okay, they're not an option. Now, what's tricky about this is this next part. It says the input values of f sufficiently close to 2 correspond to output values that are close to 6. In other words, if I put a 2 into my function, I should get 6 when I'm done. Okay? And so what's tricky about that is I go ahead and I take out the repeated factors and then I plug in the 2 and see which one works, okay? And so if we do that, on the top I'd have 2 plus 3 over 2 minus 3. That's 5 over negative 1, which is negative 5. So it can't be A, it has to be B. 2 plus 4 over 2 minus 1 is indeed 6 over 1, which is 6. So you plug it in to what's left. Okay, and that's what made that one tricky. A lot of people chose A. Why? There's a 6 sitting there. Okay, and if they weren't quite sure what to do, they picked A because there was a 6 sitting there. Okay, so, and they will always put what we call a distractor answer on there. All right, where it is a common mistake. It's just what they're going to do. All right, so unlike the ACT, when you can go, this is close. All right, that doesn't work here because all the this is close answers will be there. Okay, you can count on it. They write it that way on purpose. All right. Okay, So today we're going to talk about exponential and logarithmic functions. We're going to walk through the basics pretty quick, and then we're going to look at some multiple choice questions for these. I felt like as I was pulling questions, there were a lot more in this unit than there were from the first unit in terms of what I was pulling, okay? One of the things that I did leave is on yellow paper. This is called the Ultimate Justification Guide. So basically, to justify that something's positive or that something is best modeled by a quadratic, it tells you what the justification statement should be, okay? And this is a great resource, especially in free response. It's also good as you're working through multiple choice questions. Okay, how do I know if something is this? All right, these are the things I'm going to be looking for. So this is just a good reference, okay, for you to have. It's also on Google Classroom if you didn't want a physical copy, okay? So I just wanted to give you that because I thought it was a really good resource, all right? So here's Unit 2. Unit 2, 15 sections, lots going on, from exponential modeling to composition and inverses, logarithmic functions, equations, inequalities, semi-log plots. Okay, so just a lot of stuff that we did in Unit 2. Okay. The first thing it starts with, these are the vocabulary terms you're probably going to see that relate to Unit 2, and I just thought they were good. It was an extra included in the review materials I'm doing, or I'm using, okay? I think things that we struggled with were residuals, all right? We struggled with that a little bit, so we're going to talk about that here in just a second, what that is and how we get it. Proving an inverse, all right, was a little bit of an issue. But then I think most everything else was pretty good, okay? Most everything else was pretty good when we did it initially in terms of what I remember, okay? All right, so let's talk about arithmetic and geometric sequences. Arithmetic and geometric sequences. All right, I can get all my words to work today, okay? Remember, an arithmetic sequence is linear, right? It is a linear function. It has what we call a common difference. Okay, it has a common difference. Okay, and this is our formula, a sub n equals a sub k plus d times n minus k. It is just point slope form of a line. Okay, that is just point slope form. Right? A geometric sequence is exponential in nature. Right? It has a common ratio, meaning we are multiplying or dividing. If we divide that ratio, I put ration, that ratio is a fraction. I was thinking ratio and fraction all at the same time. Okay? So it has a common ratio. What are we multiplying by? What are we dividing by? All right, so this is multiply, divide. The first one's add and subtract. All right, from one term to the next. All right, and our geometric sequence, g sub n equals g sub k. So what we're going to start with r to the n minus k. So if I know the first term, okay, n minus 1 would be my exponent. If I know the 0th term, n minus 0 or just n. Okay, so exponential. And that's why they fit so nicely in this unit. So sequences and series. Right. Properties of exponents, again, I don't think you guys have any issues with that. If we're multiplying and have the same base, we add our exponents. If we have a power to a power, we multiply exponents. If I have a negative exponent, we drop it to a denominator and make it, not that, make it positive. And then if I have a fractional exponent, that's a root. Right? The only one it didn't list here was division, right? If I did, I'm going to put it up here, b sub m over b sub n, we would subtract those, b to the m minus n. Properties of exponents. Those will just show up, and we have to understand how they work. All right, to simplify a problem. All right. So then we jump into the actual graphs themselves. Okay. This first one we refer to as exponential growth. Okay, so that just means my base is greater than 1. Okay, my base is greater than 1. The B right there, A, we refer to a lot of times as just that initial point or my initial condition. Okay, it is always increasing at an increasing rate. Right, this one is concave up. All right, and it's concave up over its entire domain, which is nice. All right. It will always have a horizontal asymptote. And then it's in behavior. On the left, it's going to approach your asymptote. So the limit as x approaches negative infinity of f of x will always equal your horizontal asymptote. So if it's at 0, it's 0. If I've moved it up 2, it's at 2. Okay. Your right in behavior, so limit as x approaches positive infinity will always be infinity. So if it's growth, that's what it's going to do. Orange cotton candy, Carly. Nothing really exotic today. Just keeping it simple. I did a random draw out of I have these containers that have all of my packets in it, and I just draw them out. I'm all by myself tonight. My family's going to the Metallica concert. I'm going to AC/DC on the 20th. I didn't want to go to Metallica. I mean, Becca's like, she knew who the opening bands were. I got nothing. I was like, no thanks. So she's doing that. All right, other one, we have exponential decay. Okay, thing to remember about exponential decay is that your base is always going to be a fraction that's less than 1. Okay, 2/3, 3/5, 7/8. All right, so it's always a fraction that's less than 1. So when it's decay, the base is a fraction. 0.7, 0.2, 0.1, 0.000345. Right, so it's going to be a decimal or a fraction. This one decreases at a decreasing rate. This one happens to be concave up as well. So with our concavity, we're either always concave up or always concave down. When it comes to exponential functions, it too has a horizontal asymptote. And the end behavior just kind of switches. Okay, on the left this time, approaches negative infinity. It will be infinity, and on the right, it will be your asymptote. Okay. It's just basic characteristics. Look at those next to you, and I want you to tell me it's in behavior and it's concavity. So on this one, I just want its concavity and it's in behavior. Okay, what's my concavity on the first one? It's concave down. And then my left in behavior. It's approaching that horizontal asymptote. It looks like it's at 0 just based on what we've got right there, so we'll just put 0. And then what about on the right side? Negative infinity because it's going down. Okay. The other one, what kind of concavity does it have? It's concave down as well. And then my in behavior on the left, negative infinity, and on the right, 0, which is my asymptote. Okay, so just looking at those two. So exponential functions can be flipped over the axis. That would be negatives in front of those that made that happen. Okay, to flip it over it. Special exponential function with a base of e. All right, the natural base, remember that's just f of x equals e to the x. What do we approximate e as? Close, 7.1. Okay, 2.71 or 2.7. Okay. So now let's talk about transformations, okay? I didn't talk about that yesterday just because there were lots of different ways that we could look at it, and I knew it was going to come up today, okay? If we think a general exponential function, all right, a times b to the x plus h plus k, that's the versions that they use. Remember, a is your your vertical, stretch or shrink. They might call it a dilation. Okay. H is your horizontal shift. So left or right, remember we do an opposite. And then K is your vertical shift. We can also put an extra constant inside of that parenthesis where x plus h is, and that affects it horizontally, but we'll look at some of those when they pop up. Okay. Okay. Remember with that one inside parentheses with x, we always do an opposite. Okay. Okay, so one of the cool things, there's some function manipulation when it comes to exponential function, but every horizontal translation, okay, so if I move it left or right, is equal to a vertical dilation. All right, I'll show you how that works. So every horizontal translation, so I put something in parentheses with x, with the rules of exponents, will work itself out to just be a vertical dilation. Okay. In order to have added my exponents, we had to have kept the base and multiplied. Okay. H is a constant, so that b to the h is the same thing as a times b to the x. Right, that is that vertical dilation. Right, it's the same thing, it's just a constant. right, let's talk about context and data modeling. All right, if something tells me that it doubles every day, what does that make the base of my exponential function? It makes it 2, so f of d would equal 2 to the d, okay? But let's say an equivalent form says, let's look at this form of it. What do I do with this one? If f of d equals 2 to the 7th times d over 7. Those two equations are actually equal to each other, right? Because what would we do with the exponents? They would multiply, right? And so the 7s would cancel and we would get d. Okay, so they are equal and you can... Right? Remember when we do half-life problems? What's your base on a half-life problem? Not a trick question. 1/2. Okay? Your base will be 1/2, but you always have to restrict the exponent. Okay? So it's always t divided by amount of time for that half-life. All right, so it might say the half-life is 23 days. So you would take t and divide it by 23. Right, so if you ever run across a half-life problem. Divided by amount of time for the half-life. All that should be under that. You're going to restrict that exponent. Okay. Now, remember, this is where we could do a regression, all right? So for calculator, if they ask me to do a regression, or we would use EXPREG. All right, so that's calculator. If they give me a set of data and they tell me to get an exponential model, that's what we would do, all right? And it's through that exponential model that we get residuals. Okay. And a residual, all right, is the actual data value minus the predicted. So predicted means I put it into my regression. Okay, so a residual is the actual value minus the predicted value. Okay, now in order for a model to be a good fit, there is no pattern in the residual plot. So if you see a residual plot, it will say residual plot. It should look like chickenpox. Okay, there should be no pattern. Okay, so no pattern in that residual plot, and you can't do a residual plot until you get a regression. Okay, no pattern in residual plot equals good fit. All right, it's how we judge it. Residuals are the only way to judge whether or not something is a good fit. And we'll look at one here in a second. What are they watching?
It sounds like you're like a movie and a comic movie. Yeah, like there's a Kahoot that way, and then there's like some random movie. Oh, because it's playing with the background music.
Oh, it's a Kahoot. So it must be, no, she's got planning. Well, this one back here has planning, so it must be somebody in this room. No.
Get her free time.
Yeah, well, this is what I'm going to do. Okay, so let's talk about composition, all right? Remember your notation, f of g of x, or f of g with a little o and the x. You could see them both, all right? It's a two-step process. Work your way inside out. There's not a class that meets in there right now. So only this room.
Who's in there then?
Oh, there's people in there. She babysits people.
I see like people come into like our room to go into there sometimes.
Well, wave. Oh, with a slime trail, I see. Okay, creativity at its finest. Narwhal. Okay. I just keep guessing other animals. Okay. All right. So now let's get to inverses because inverses are a big thing. Okay. Inverses. One of your free response questions that you did in your practice test asked, how do you know that the inverse exists? Okay. In order for an inverse to exist, all right, the function must be 1-to-1. And that's the statement you have to say. Okay, now that means it has to pass a horizontal line test, all right? But you can't say horizontal line test, they will not give you credit. You have to say it's a 1-to-1 function. Okay, that it must be 1-to-1. So in my brain, I'm going to think horizontal line test, but I'm not going to say it. Okay, now another thing that I'm going to think because of inverses is that the x's and the y's switch, which means the domain and the range switch. Okay, but the only way to prove an inverse, you have to know that it's 1-to-1, or you do the compositions. And remember, f of f inverse should equal, if I switch them, f inverse of f, and they should always reduce out to a plain old x, okay? That's how we prove it, that it's true. It equals what we call the identity function. Okay, so that's how we're going to do inverses. Remember, if we want to find one algebraically, which you may be asked to do, we switch x and y and solve for y. Okay, so that's the manipulation process if we need to physically find an inverse. So it just depends on what the question would ask. It could ask you any combination of all that mess up there. Could give you a graph and say, what is the range or the domain of the inverse of this graph? So you would have to know, okay, this is the domain. It has to be, if I'm looking for the domain of the inverse, I need the range of the first one. Okay, so they could ask those questions in lots of different ways. I think we're going to do one here in a second. I put that in the multiple choice, I'm pretty sure. Because I saw it last night. I was like, oh, that's a good thing. I want to be sure I say that. Okay. All right. So once we get through inverses, then we can talk about logarithms. Remember, logarithmic expressions and functions are inverses of exponential. Okay, so if I have y equals a log base b of x, remember we can shift it just like we always could. All right, and do all those things. But that round robin, so if I have log base b of x, that equals y, then b to the y equals x. We can just write it either way. Okay, so we can write them either way. And we use that concept of going from logarithmic to exponential to get through to all this stuff. Okay, a common log has a base of what? 10. We don't see it. Okay, so that would be like log of 100. All right, that would be a common log. A natural log has a base of what? E. Okay, it's a base of E, but we don't see it. We see ln instead. Okay, so a base of E. So a natural log is a base of E. Now, when we look at graphs of log functions, we have to remember it's an inverse of an exponential function. Okay, an exponential function has a horizontal asymptote. Guess what this one has? It has a vertical asymptote. Okay, so it's always going to have a vertical asymptote, right, which is nice. If I look at this one, I would say that it's increasing at a decreasing rate. Right, so it's going up, but it's leveling off as to how much it grows. The second one would decrease at an increasing rate. First one will be concave down, and it's going to do that over its entire domain. The second one would be concave up. That would be over its entire domain. So it's going to do the same thing the whole time. It doesn't do some curly Q's and switch concavity. Okay, it stays where it's at. And then for our end behavior, right, the limit as x approaches, this time we have to approach the asymptote. All right, so we approach the vertical asymptote. Right. Now, if I'm approaching that vertical asymptote, I'm going to come in from which side, the right or the left? The right. So I'm going to put a plus right there. Did you say left? Yeah. It's okay. Of f of x. Okay, and this one's going to go down, so it's going to go to negative infinity. The other one, as I approach positive infinity on the right. Okay, so positive infinity. It's going up, so it would be positive infinity. So I think end behavior on these is a little tricky. Right. But the good news is the left side is always the limit as we approach the vertical asymptote from the right. That doesn't change. Okay, of g of x, it's getting closer and it's getting bigger and bigger, so it'd be positive infinity. And then the limit as x approaches infinity, so on the right side, it's going down, so negative infinity. And I think that's the hardest part. I think log graphs are probably one of the hardest we do, outside of those crazy trig graphs where we have to change the periods and all that mess. Almost done. Okay.
Why do you have the little plus by the vertical?
Because we can only come to the vertical asymptote from the right-hand side. So that's what that means. That little plus means I can only approach it because everything's on the right-hand side. I'm not over on that negative
Okay,
side.
I thought you were asking what side we were doing. I was like, oh, we're doing a left. Never mind.
Okay.
Never mind. It's okay.
You're good. All right. Properties of logarithms. These you will see, guaranteed. Okay. If I multiply, how do we separate them? Addition. So log base b of a plus log base b of b. Okay. If it's division, they didn't put that one on here. I'm going to write it underneath. Log base b of a divided by b, how do we separate them? Subtract them. Okay, so log base b of a minus log base b of b. If we have an exponent, what do we do with that? Yep, move it out to the front. So x times, nope, n times log base b of x. Okay. And this last one, you're probably thinking, I don't see anything to change about that. But this is what we use called change of base, which means I could use a common log of what's inside the logarithm, that word, over the logarithm. All right, the logarithm of the base. Okay, so you can use common log, you can use natural log. All right, you can use log base too, as long as they match, it doesn't matter. Okay, so that's change of base. And we don't use that one very often, but it will show up periodically. All right, cool beans, getting close. Okay. So all our properties. All right, how do we know it's an exponential function? Looking at the table. Okay, here's the dill pickle on that. Okay, equal length intervals on your inputs. Okay, so your x's are equally spaced. Outputs are proportional. Okay, and proportional just means I multiply or divide by the same amount. Okay. So since exponential and logarithmic functions are inverses for a logarithmic table, we switch that, okay? So the inputs are proportional. And the outputs are equally spaced. And I think that's just the easiest way to remember that. Okay, if you remember one, then the other one's switched. I really want a Ring doorbell so I can buzz people in.
Buzz people?
Yeah.
I'm like, hi, hey,
It's you.
Does that make you think like, who are you? Like, I want to pick which when I go?
Maybe he's there.
I understand why he's using it as an excuse, but it's also like, for asked to be honored. You don't say, you know what, I
That's
actually,
good, but let's do it another day.
I'm okay with you honoring me, but let's honor me on my terms.
It's not like,
Right?
it's not even my dad.
I don't think that was the intention.
I know not, but I'm just saying.
I've been hiding it.
It's Miss Craddock. She's so funny. Oh, yep, that's her. All right, so just like with exponential functions, we can manipulate with the properties and we get different things, okay? So one of the things, every horizontal dilation equals a vertical dilation. Okay, so here's what I mean by that. Okay, so a horizontal dilation, come on. Okay, means there is a constant inside the parenthesis next to x, okay? That's a horizontal dilation. If we use the properties of exponents, it would say, hey, bust that bad boy apart with addition. Okay, well, log base b of k, that's a log of a constant, would just be that constant. Okay, so it becomes a vertical dilation. I would move it up or down. I would actually call that a vertical translation. Sorry. Just didn't like the word. right. Okay, so then we get to equations and inequalities, all right? And there are lots of ways to solve these, okay? My favorite is that I have same base, all right? Or I could rewrite to the same base. All right, so something like 2 to the 3x plus 1 equals 4 to the x minus 2. All right, made that up. If the bases are equal, then the exponents are equal. All right, same is true for logarithms. If I have log base 2 of 3x minus 1 equals log base 2 of 7, okay, as long as the bases match, 3x minus 1 would equal 7, and we could solve from there. That's the most common, all right, method. Thank you. All right, there's some delay there, all right. But with that exponential one, right now the bases don't match. Could I fix it so that they did? Yeah, I can rewrite that 4 as 2 to the second. So I have 2 to the 3x plus 1 equals 2 to the second to the x minus 2. So I could say 3x plus 1 equals 2 times x minus 2 and solve from there. Okay, so that's the most common way to solve exponential and logarithmic functions. Unfortunately, that don't happen too often. Okay, it just doesn't. Remember, we could always take something like this. 3 to the x minus 1 equals 4. Okay. We could rewrite it in log form to solve it, okay? Rewrite it in log form. So the base of the exponential is the base of your logarithm, okay? The 4 would go inside, and it's equal to the exponent. So then you could solve, okay? We could also do that the opposite direction. Log base 7 of x plus 2 equals 3. So we could rewrite that, 7 to the third equals x plus 2. So we can get it into some form that it can solve. Okay. The last thing you have to remember is that there can be extraneous solutions for log equations. Okay, and we just have to be careful, all right? We have to check that we don't end up with negatives inside the logarithms on the original problem. That typically happens if we end up with two logarithms that I have to put together as multiplication. It becomes quadratic, something like that in the process. All right, that's when that could happen. Nothing like reteaching you a month of material in a day. All right, last two things that we talked about were modeling with log functions. That's going to be on your calculator. All right, it is the LNREG. Okay, that's the one you will use is the LNREG, not LOG. All right, don't use that one. All right, it's LNREG. Okay. And then I just gave you an example. Did I give you an example of a simulog plot just as a reminder of what it looked like? Okay. Yeah, that was the easiest thing in the whole thing, right? I agree. Well, right now, we'll probably get one question. I know. That's okay. We're going to get that one. And that's one more than we would have gotten otherwise. Okay? Just saying. That sounded terrible, didn't it? Now back that up. Back up, flip it, and reverse it. Okay. Okay. All right. So remember with this one, this is calculator. And you're going to use LNREG. Don't use the log one. All right. And it's always y equals a plus b ln x. That's what that equation will look like when you grab it. Okay. And then a semi-log plot. All right. Remember that it's in powers of 10. Okay, so the first one goes 1, 2, 3, 4, 5, 6, 7, 8, 9, then 10. After 10, it would go 20, 30, 40. It counts by whatever's there. Okay, so 1, 2, 3, and 4, so on. Okay, and then 40, so that's your semi-log plot. The main thing to remember about a semi-log plot is that exponential data is linear on a semi-log plot. That's the big thing they want you to get out of that. Can you plot a point and tell me if it's exponential? All right, and we'll know it's exponential when we get linear. Okay. All right, let's do a few practice before we go. We won't get them all done, but that's okay. Right? They really like these questions of can you rewrite it to match what's here? Okay, so lots of things that we can consider here. All right, I've got 9 times 25 to the x. All right, so well, let's see what works. All right, what do you think? 25 we could rewrite as what? 5 to the second. And I've got a 9, and I could keep the x. So what's my correct answer going to be? D. Yeah, correct answer is D on that one. So you're just using properties of exponents. They like that one. Okay. That next one that we see, all right, which of the following is equivalent? Properties of logs. What are we going to do with these constants? Pull them up. So I'm going to get ln of x squared minus ln of y cubed. And now that it's subtraction, what are we going to do? Divide. Ln of x squared over y cubed, which would give me a. All right, so properties of logs. Those are nice when they happen. Okay. The next one's a transformation question just because we hadn't done one. Okay, and we needed to do one. So it gives me this random function. Think about your posters you did in here. Okay, that are out in the hallway. How are we going to move this whole picture? Left 1 and down 2. So it's pretty easy to check a couple of points. Okay. To go down 2, and then we need to scoot it over left 1. Which one's going to give me that? It is A. It is A. So we're just looking at that transformation. All right, here's one with a table. Okay. All right. Tells me it's exponential. Yay. We're trying to decide, is it growth or decay? All right, so what we've got to think about is how is it changing proportionally, okay? The fractions freak me out. I'm going over here to the 3, the 6, and the 12. What am I doing? I'm growing. I'm multiplying by 2, okay? I'm multiplying by 2. So it is exponential growth. It's got to be C or D, all right? Is it true that the B, which is the same thing as your ratio, is between 0 and 1? Yes, back. That brown box. Okay. So is the base between 0 and 1, or is it greater than 1? Greater than 1, so it's D. Okay. That's what matters on that one. All right. It is growth. We are growing. Okay. All right. Let's look at 11. Okay. So this time it wants me to do a composition. All right, f of g. So what we're going to do is we're going to take this g function, and everywhere I have a variable in f, that's what I'm going to put there. Okay, okay. So I'm going to do f of x minus 3 over x, which says We're going to take what's ever in there, x minus 3 over x. We're going to square it, and then we're going to add 1. Now, obviously, they did some stuff on here, okay? My hope is that it's c, but I'm going to double check it real quick, okay? I'm going to actually square that first fraction, all right? X minus 3 squared would give me x squared minus 6x plus 9, that's the one, over x squared. So just to double check myself, it would be c. Okay, so we're doing a composition there. All right, for 14, okay, this function has the property that for each time the input value doubles, the output value increases by 1, okay? And I did this one on purpose, okay? So each time the input value doubles, the output value increases by 1, okay? The input doubles, the output increases by 1. Think about that one for a second. This one's a little bit tricky. So let's check it. My input would be 2. My output is 1 on that one. So if I double it, that's 4. What's my output? 2. Okay, my input, 6. My output should now be 4. Did we hit it?
No, they would have to double it, so it'd have to.
Oh, it'd have to be 8. Sorry, 8 and 4. Did that work? Yes. Okay. If I look at the other one, at 2, I got 4. At 4, I did not get, okay, what I need. Does that make sense? It didn't go up by 1, so it has to be B. But you can check them that way. All right. I would just do what it says. All right. All right. 18, composition with a table. Okay, composition with a table. We want to do f of g of 0. Start on the inside. What is g at 0? 1. So now I want to do f at 1, which would be -2, which is A. Okay, so just follow the table. Okay. All right, 22. Okay. It tells me that we've got followers in thousands for a new musical group on a social media site. We want to construct a model to represent these data. Which of the following best applies to this situation? Well, why can it not be linear? Because the first two options are linear. I go up by 10, I go up by 15, I go up by, right? So it's not going up by a constant amount. So that's why it can't be linear, all right? Those are not an option, all right? So the thing I have to figure out is what's my ratio? Is it 2/3 or 3/2? Easiest way to check it, y2 divided by y1, okay? 30 divided by 20 is how much? 3/2, so it's D, okay? If we can pick out that it's not linear, okay, the quickest way, all right, to get that ratio, especially with decimals, is to divide. And I'm definitely using 30 and 20 and not everything else. Okay. All right, let's do a log equation. I've got log 10 of x minus 1 plus log 10 of x plus 3. I want to find where these two things intersect. So log 10 of x plus 9. Okay, if I can get a single log equals a single log, I can drop the logs. Right? How would I put that left-hand side together? Multiply x minus 1 times x plus 3 equals log base 10 of x plus 9. Good news, they're both log 10s. I'm going to drop it. So it's going to give me an x squared plus 2x minus 3 equals an x plus 9. It is quadratic. I'm going to make it equal 0. X squared plus x minus 12 is equal to 0. We're going to factor So we get -4 and +3. Okay, we get -4 and +3, but it's log. What do we got to go back and do? Check it. Okay, check it. I'm going to put that -4 in at the top. -4 minus 1. That don't work. Okay, check your 3. 3 minus 1. 3 plus 3. 3 plus 9. So it's only A. Okay, and that's what most people miss on that one. Okay, you got to check those extraneous solutions for your log equations. Okay, these last 4 are calculator active, which is good news. All right, because the data here is, bleh. All right, it's a little bit nappy. Okay, it's a little bit nappy. 79 we can do without a calculator, which is nice. It's that semi-log plot. That's the easiest thing we did. Okay. But let's take a look at this first one. Okay. So it says in a certain simulation, the population of a bacteria colony can be modeled by a geometric sequence where the first day of the simulation is day 1. The population on day 4 was 4,000, and the population on day 8 was 49,000. Okay, we want to know what it is on day 6. Okay, so because it's geometric, all right, we can say this: 4,000 equals whatever we started with times our ratio to the t minus 4. Okay, to the t minus 4. Okay, the good news is it gives me some things to help me. All right, it gives me some things to help me along the way. All right, how could we figure out, or what would I need to do from here, all right, to figure out how it's changing in terms of our growth rate? Anybody know? Because that rate, there's a way to do it, if you remember from Algebra 2. It involves a radical. Okay, we can't do it like we do a linear function where we could just do slope, right? So what we're going to do is this. Let's find the difference between those values, okay? So what's the difference between 49,000 and 4,000? 45,000, okay? Now, how far is it from 4 to 8? 5, 6, 7, 8, right? How many numbers is that? 4. So my R is equal to the 4th root of that difference. Okay, it's the 4th root. So they're 4 apart. It's the 4th root of that. So I get 4,000 equals A times the 4th root of 45,000 times t minus 4. Okay. The next thing we got to do is solve for A. We got to have that initial amount. All right. So we would plug in this ordered pair and solve. Okay, we would plug in and solve. For A. And then go from there. Okay, all right, we're about to run out of time. This one, could you pick it out? Which one can it not be for sure? A or D. Okay, because those aren't even log papers. My guess is that it's C. 1's at 30, 2's at 50, yeah. Okay, all right, we'll talk more about the calculator stuff. The only thing I left you to do in terms of extra practice, we won't do the wrap up today because it's time to go, is the session 2 AP Daily. Okay, again, those aren't very long. I think it has 4 problems on it today. To go in and watch that little video and just listen to them explain what they're doing, okay? We'll start tomorrow with a 5 for 5. Okay, and then we'll go right into Unit 3, which is all the trig stuff. Okay, hopefully we can move through that pretty quick since we just finished it. Okay, thanks y'all. You did good today.